If you want to build a continuous time inverting amplifier, the math is straightforward. You take an op-amp and set the gain using the ratio of two physical components, a feedback resistor and an input resistor. It is a reliable, standard analog design. But when you try to print that classic design onto a modern CMOS wafer, you hit a strict physical bottleneck. To keep power consumption low while hitting precise high-gain targets, those physical resistors have to be huge. On the actual silicon, high-precision polysilicon resistors consume massive amounts of expensive die area, often completely dwarfing the op-amp itself. Worse, the manufacturing process makes it incredibly difficult to get two separate physical resistors to match perfectly across the board. The industry solution was to stop using physical resistors entirely. Instead, engineers replaced them with capacitors and a network of precisely timed switches. In semiconductor manufacturing, capacitors can be fabricated with highly accurate relative sizing, meaning their ratios match beautifully on the die. To save area and guarantee mathematical precision on modern silicon, designers had to let go of continuous flowing currents. Instead, the architecture moves to a discrete time system, trapping and transferring tiny, exact packets of charge. This schematic and accompanying waveform show the baseline architecture of an ideal switched capacitor amplifier. We have our op-amp, two capacitors, C1 and C2, and four switches. The entire system is governed by a two-phase clock. Critically, those two clock phases must be non-overlapping. The input and output switches can never be closed at the exact same time. During phase 1, the sampling phase, the input switch is close. The primary capacitor, C1, connects directly to the input voltage. It fills up with charge until it perfectly matches VIN, while the output path remains completely disconnected. Then comes the moment the clock toggles to phase 2. The input switch is open, trapping that sampled charge on the plates of C1. Immediately after, the second set of switches closes. Because the op-amp maintains a virtual ground at its inverting input, that entire trapped charge packet is forced out of C1 and flows directly into C2. Because the op-amp input has incredibly high impedance, the charge literally has nowhere else to go. By strictly conserving that charge packet as it moves across the circuit, the resulting output voltage is determined purely by the ratio of C1 over C2. By strictly choreographing the movement of a trapped packet of charge from one phase to the next, we synthesize precise voltage amplification, all without a single physical resistor. That is the mathematical ideal, but ideal massless switches do not exist. On an actual chip, those switches are physical NMOS transistors, and they obey the messy rules of device physics. This plot of V out versus time, alongside the transistor cross-section, shows what happens when we drive the gate high to turn the sampling switch on. The transistor moves from saturation deep into the triode region. To conduct, it has to physically build a channel of charge right under the gate. As long as the switch is closed, that channel sits there, holding electrons. The physical failure happens the millisecond the clock drops. To turn the switch off, that conductive channel must collapse. As the channel disappears, the charge it was holding is violently expelled, pushed out of both the source and the drain. Half of that expelled channel charge flows harmlessly back toward the input, but the other half injects directly into our high-impedance sampling capacitor. This extra burst of electrons corrupts the total charge packet, permanently altering the exact voltage we just spent the entire phase trying to sample. The elegant equations of the ideal amplifier break down immediately on real silicon. To make this work, we have to physically trick the transistor into mitigating its own parasitic charge injection. The hardware fix for this is the dummy switch. It is an extra transistor placed immediately adjacent to the primary sampling transistor, with its source and drain deliberately shorted together. This dummy transistor is sized precisely to be half the width of the main switch, and it is driven by the exact opposite clock phase. As the main clock drops and the primary transistor turns off, expelling its error charge, the inverted clock goes high, turning the dummy switch on. By turning on at that exact moment, the dummy transistor creates its own channel. Because it is half the size of the main device, it acts as a vacuum, absorbing the exact quantity of error charge expelled in direction before those stray electrons can ever reach the sampling capacitor. Robust IC design requires building secondary, parasitic structures right into the silicon that perfectly mirror and cancel the physical flaws of the primary devices. Once you can accurately transfer charge, you can scale the concept up to perform arithmetic. This schematic shows a multiply by 2 circuit. During the initial sampling phase, both C1 and C2 are connected to the input, allowing both to track the voltage simultaneously. Then we move to the amplification phase. The left plate of C2 is suddenly switched to ground. Because the charge cannot escape the high-impedance loop, fully discharging the second capacitor forces its entire stored payload directly onto the first. We have successfully pooled both packets, doubling the charge on C1 and exactly doubling the output voltage. This graph shows the output voltage waveform stepping up in a staircase pattern, mapped directly to our next logical circuit, the switched capacitor integrator. By modifying the feedback loop so the second capacitor remains continuously connected across the op-amp, the circuit no longer resets. It accumulates charge cycle over cycle. As this chart shows the waveform generating step by step, you can see that with every single clock cycle, the circuit adds a precise voltage step to the existing total. The exact height of that step is determined strictly by the ratio of C1 to C2 and the previous input voltage. That staircase waveform is the highly precise, discrete time equivalent of a continuous mathematical integral, executed entirely in hardware and fully immune to the matching errors of physical resistors. There is one final physical threat to resolve. The actual silicon routing on the die and the bottom plates of the capacitors naturally create their own parasitic capacitance with the substrate. Left unmanaged, that invisible parasitic capacitance will passively absorb signal charge out of the loop. The ultimate topological fix is the parasitic insensitive integrator. By strategically rearranging the order of the input switches, engineers ensure that the sensitive plates of the capacitors only ever toggle between physical ground and the op-amp's virtual ground. Because the voltage across those parasitic components is always held near zero or aggressively driven by a low impedance source, they can't absorb any extra electrons. The exact sequence of the switches isolates the main charge packet from the physical flaws of the silicon floor. This block diagram shows a complex mixed signal system, and right here in the center, the microscopic parasitic insensitive integrator serves as the core building block. Once perfected, these integrators are chained together to form massive arrays, like the sigma-delta analog to digital converters used globally. High-fidelity audio in your headphones, the sensor data in your phone, and the backbone of modern telecommunications all rely on translating the physical analog world into digital data. That translation only happens because engineers learn to replace continuous flowing currents with the precise mechanical choreography of discrete time charge.
Thanks for watching and grow every day with just a bit of information. Like and subscribe for more content and learning.